All right, welcome to your favorite class. This is Calc 2. My name is Ron Patton. Today we're going to talk about particle motions of parametric equations. This is video number 10 in this series. All right, so the motivation, well, we'll now discuss motion along curved paths. And I love this because we're talking about physics, so we get acceleration, velocity. It's just a lot of fun things. So our position vector is going to be r of t. Okay, and it's of the form this x of t I, and I just means it's going in the x component, okay, along the x-axis, and then y of t, j, and that j just means that you're going up on the y-axis, okay? So what does that mean? So sometimes it's easier if we just get a definition. So if we take a velocity vector, it's pretty standard. You just think of it as its first derivative um, of of your position. So anyway, you just take first derivative position, acceleration is second derivative position, and then the unusual one here is the speed. But if you think of it like Pythagorean's theorem, the speed or magnitude is going to be the square root of your x component, the change in your x component, and your change in your y component. But each of those are going to be squared, and then you add them together and take square root. So it's like you're getting this it's like the hypotenuse of a triangle, okay? But you're taking um, these distances in order to figure it out. All right, so let's get into example one. All right, so a particle moves along a plane, curve divided times this. So 3 sine t divided by 2 for the I component and 3 cosine of t divided by 2 for your j component. All right, so let's sketch a graph of this first. All right, so what I would do is I would just make a quick table. Okay, so I have my t, I have my I component, I have my j component. So let's make it easy. So if I have 0, then we're just plugging this in. So for 0, the I, since it's sine, is going to be 0, and the j component is going to be 3. So since I have t divided by 2, I'm going to have like pi for my next piece. So if I have pi, that means that it's really pi divided by 2. Sine of pi over 2 is actually going to end up being 3. For your cosine or j component, it's actually going to be 0. So now let's just keep on going up. Easy ones like 2 pi, we'll do 3 pi, and then we'll do 4 pi. All right, so if 2 pi, you should get 0 and -3. You should get -3 and 0. And then the last, is that right? Oh, and then the last one is where we started at, 0, 3. All right, so if we draw this at time is equal to 0, we get 0, 3. So that's where my dot or my particle is going to start. And then if I go over here at t is equal to pi, it's gone in a curve over to that. And then literally, if I'm drawing this, it's just going to go around. So you think it should be a circle, and it ends up, yes, it is a circle. And then you start exactly where you stopped. All right, so anyway, we've sketched a path of the particle. Now let's find the velocity vector. So velocity vector would be v prime, and all that is just a first derivative. So we have 3 halves. We'd have a cosine of t divided by 2 for the I component. And then I have minus 3 halves times the sine of t over 2. So remember, if you take a derivative of cosine, you get a negative sign, and that's for our j component. So what about acceleration? Yeah, let me just fix this. So this is really v of t, and a of t is going to be, it's very similar. So we should have a -3/4 because we're taking the derivative of cosine, which is a negative sign. T divided by 2 for the I component, and then we have a -3/4 cosine, cosine of t divided by 2 for the j component. All right, so now the final thing on this one is our speed. So it's the magnitude of velocity, which is going to be equal to the square root of 3 halves cosine of t over 2. That whole thing is going to be squared, plus a negative 3 halves sine t divided by 2. That whole thing is going to be squared. All right, so now the nice thing that we can do is we're squaring 3 halves, and then we're taking square root. So I'm actually going to factor that out. And then I've got the square root of cosine squared t divided by 2, and plus, because the negative times negative is plus, sine squared t divided by 2. Um, so if you remember your trig identities, this piece right here is just 1. So our final answer for velocity, or the magnitude of that, no matter where you are, what time, is always going to be 3 halves. All right, so hopefully it makes sense. Now let's get to example 2. All right, so example 2 is an application. So, and this is baseball. So let's says baseball is hit 4 feet above the ground and leaves bat at a speed of 105 feet per second. Pretty hard at an angle of 40 degrees to the ground. All right, so let's get our uh, our motion of the ball. So R of t is going to be equal to, so we need to do our x component. So our x component is going to be this, it's hit at 105. It's the cosine, because that's on the x-axis, 40 degrees times t. And this is your initial velocity. And then that is for the I component. So for your y, so we got to take into account gravity. So it's 16t squared. And then we have 105 sine, because we're in the y component now, 40 degrees times t. And then we can't forget about the 4 feet. So this is gravity. This right here is your initial velocity, and this is your initial height. And that's all in the J component. All right, so how high does the ball go? So the first thing that we gotta see is y prime is equal to 105 sine of 40 degrees. We gotta see minus 32 t. So I'm just taking the derivative of that. So if I set that equal to 0 and solve for t, then we get 2.109 seconds. So now I just got to plug that into our original height. So the height is equal to y of 2.109. And if you plug that in, you get negative 16, 2.109 squared plus 105 times 2.109 times the sine of 40 degrees plus 4. And that is going to end up being 75.176. So it's actually pretty far up. Okay. So now there is a 12-foot high fence, 325 feet from a home plate. Is this baseball a home run? All right. So to answer that, we have that. So let's figure out our x. So x of t is equal to 325, and that's equal to 105 cosine of 40 times t. So if we solve for t, we get t is equal to, it took 4 seconds, a little over 4 seconds. So now y of 4.0405 seconds. If we plug it into this exact same thing up above, so it's negative 16, 4.0405 squared plus 105, 4.405 times the sine of 40 plus 4. then we actually get 15. So it's going to be at a height of 15.494 feet. So the answer is yes, that is a good hit, and it's a home run. Woohoo. All right, so it's a home run. All right, so that's awesome. Using math to figure it out. It's awesome. All right. So now on this one, I want you to try it out yourself. So this is a particle that's moving along the plane given by the following motion. All right, find the velocity and the acceleration vectors, and then plug it in for the speed at t is equal to 0 and t is equal to 2. So please put this on pause. Um, and then in a second, once you figure it out, replay it. So for this one, the velocity vector, I just felt like writing it out by hand instead of actually putting it on. So the velocity vector ends up being v of t is equal to 2t for your I component plus 1 for your j component. And then a of t is equal to 2, which is derivative 2t I. There's no j component. And then for the speed, so the speed for any t is going to be the square root of 2t squared plus 1 squared. And if you plug in 1, if you plug in 0, 0 for that, you can see that it just goes to 1. If you plug in 2 for it, you get 16 plus 1, which is square root of 17. Right. So hopefully that helps. Now you should practice the homework and just do your best. All right. All right. Thank you very much and giddy up.